Hello and welcome. And I'd like to say that we have a good news. Good news, everyone. Yesterday, after the stream, I was trying to start this Physarum project, and on about 2 hours stream, I was able to do almost nothing. Well, after that stream, I had a lunch, uh, gather all my thoughts together and was able to implement this thing. What? What's wrong with you? Ah, I guess it's something about something about credentials. Whoa. Okay, so let's just restart it. Whoop. And while we're restarting Xcode, I'll I want I want to I want to announce that this project is available on GitHub. Pull requests, suggestions are welcome. Well, the code is complete garbage and mess, and it requires a lot of improvements. But it works. Ta-da! Actually, yeah, it works. Isn't that beautiful? So we can we can relax and stare at this animation, simulation, whatever it is, for some time. But actually, let's go through the code to see. Actually, I do not need this headphones because I have my audio monitoring turned off, because I still have no way to low latency audio monitoring, and I still have no way to capture audio from the computer itself. So if there is a music playing on this MacBook I'm streaming from, I can hear you. You cannot. Sorry. No music yet. But need some kind of hardware mixer. So, code. Um, Walking through a code. So we did basic setup yesterday. we have a view controller that has a renderer field, and we using the views, actually the view controller's view based on MTK view class type, and we define drawable size. All these constants should be parameterized from outside. It's like a lot of things to improve, as I said. So we have this metal view, and we pass this metal view to renderer. And on renderer, we do next thing. We define clear color for this view, and we set this renderer as a delegate for metal view. And to be able to set renderer as metal view delegate, we need to conform to MTK view delegate interface, so how it called in Swift, protocol, I guess. Is it protocol? Any tooltips? Xcode. Options click. Option click. Methods for responding to a metal key views drawing and resizing event. MTK view delegate. Okay. Drawable size will change. We need to hook up this thing as well. But those are details. Let's stick to the main topic. So I defined a particle. This is a thing that moves around an area, and this thing like this. This particle left some residue, some substance on a plane, and every frame this substance is being spread out with a blur, and particle has like 3 sensors, one in front of it, like yeah, it has a direction, and this direction defines movement direction of a particle, and also it defines, based on these directions, there are 3 sensors, like left one in front of, and in front and a little bit to the left, straight forward and forward and right sensor, and particle samples the substance density, like substance density from these sensors points, and it decides to make a turn to the direction with the most intense value, something like this. And the intensity is like intensity of the residue what that is left by this particle. I hope it makes sense, but and Tagma has a great tutorial. Actually, this first mm, first part of their Physarum simulation is a good explanation of the mechanics this effect has. So, here we do some initialization. We set up our device, command queue, and here we initializing particles. Like I'm creating 2000 particles with a random position within our texture with a random value for direction. Actually, as it's not normalized, it has different direction could also define a speed. So basically it's a vector of speed and intensity. I do some like I go over one that usually used as like we have floats for colors between 0 and 1, but here I want to have a little bit more intense places. So all these parameters should be tunable from user interface, and user interface is one of the things to implement. So we have particles and we need a way to send them to GPU. So we creating a buffer using device. Please make us a buffer with particles as bytes, and we provide this memory layout thing to define a length of a buffer, and we do not need any options here. Vertex, as we saw yesterday, those are for creating basic two triangles to form a plane where we will draw a texture that we generate with compute shaders. So we make a library and creates functions. So this kernel function is to simulate particle moves, and fragment function to draw a texture resulted to draw a texture we have from simulation on this plane. Vertex function is to put vertices in the proper places and set correct UV values for them. And blur function is a second step of simulation where we do blur and spread out of this residue. Okay, so here we're creating a first here we creating a descriptor for compute pipeline. And here we setting two compute functions. Actually, does this makes sense. I'm not sure. Actually, I'm not sure if this makes sense. And if I do need this, because I guess I need only descriptor, and then I can actually I do not need a compute pipeline descriptor. I can create compute pipeline state right from the device, passing a function to it. Right, I do not need this. Okay, it's rubber duck debugging way. Let's check if it still works. It works perfectly. Okay. So we created a render pipeline descriptor. This one we need. We set functions for it. We set color pixel format. And here we're trying to create pipeline states for rendering, for computing first step using kernel function, and for computing second step using blur function. We'll take a look at these functions a little bit later. Here I'm creating a texture descriptor to create texture to draw on with compute functions, and to draw this texture using fragment fragment shader. Okay, so we need this. As we do not need to write to this texture from our CPU code, from our Swift code, we can set it as a private storage mode, but we need shaders being able to write to this texture. So we need to set up it as shader write and shader read usage. Okay, we set in dimensions of this texture, hard-coded. Need to fix it. And we build in a texture using this descriptor. Okay, so drawing. So some kind of initialization. As I know it's a lightweight thing, we already have these things available, as I guess. I need to check it later. So just getting references. It's quick and easy way. And here we're setting up render encoder. We initializing it with render pipeline state. We created earlier. We set in vertex buffer for our planes. We're setting texture as a fragment texture to display on this plane created by these vertices. We were saying like draw this vertex buffer as triangles starting from the first vertex and 6 vertices total. And that's it for, let's say, rasterization part. And here we set in the blur step. We creating a blur encoder. It's a compute command encoder. We set blur pipeline state, which has blur function within it. And and here we set a texture we want to process available for this encoder, for this blur kernel function. And here we doing some preparations to prepare a number of threads and thread groups to be able to process them, to be able to process this texture in parallel as efficiently as possible. It still looks like some kind of magic, but I guess soon I'll be able to write this thing not by example, but understanding completely what is happening here. Next, we say that, okay, get ready. Here we say that we complete setting up this blur encoder, blur step. And this is the compute encoder for the particle simulation step. Here we're deciding in this compute pipeline state which has a kernel function as a function. Here we're deciding where, in which direction should particle turn, or should it just go straight forward. And we advance this particle forward, and we left a teeny dot of residue, which on the next frame will be blurred with this blur pipeline state. And encoding. And here we dispatching threads in a little bit more obvious way, while a texture here that has been processed by blur pipeline state is two-dimensional. So we can set our threads like a grid, as we have here. So we have some thread grids and thread grouped by some chunks to process this 2D texture efficiently. Those particles are just plain 1D, one-dimensional array list of particles, so we can just set it has a particles count with everything else left, like with 1. So we have one-dimensional number of threads processing each particle, 1 thread per particle. And so let's take a look at these shaders. So this is the vertex structure. We talked about it yesterday. It's for vertex function. This vertex function returns a vector with position and UV value. UV value is calculated kind of in a straightforward way, and it's not like necessary to implement this thing in the shader. We just could have this additional values being set up in a vertex data, and we just pass it through without any modification, but as there are only 6 vertices, there is not a lot of processing being here. So next thing is a structure for particle. It's basically same thing we have here, just to conform data layout. 2 floats for position, 2 floats for direction, 3 floats for intensity, RGB. And this particle actually is being used in this compute function, which is this function, kernel function, that is used in compute pipeline state. So this function takes texture we created as thing to write to and to read from. It has index 0. It has particles from device memory, like something memory access, uniform memory access, buffer index 0. Like it has structure of particle and it's kind of array of them. And this is like thing I'd prefer not to show to anyone, but it works. So here we have some matrices defined, like this matrix is kind of identity matrix for moving forward. It does, when I apply this matrix to directional vector, it will not modify it. So if you need some insights on a rotation matrix, this is the way you create a two-dimensional rotation matrix. So basically this is cosine of 0, like moving forward. We do not want to rotate it anywhere. This is like a minus sine of 0, 0, whatever. Should be like minus whatever. It's still 0. This is the sine of 0, and this is cosine of 0. Here I'm defining an angle for rotation as in a Physarum as a Physarum particle, Physarum actor. Let's open it. I guess maybe it has some illustration here. So Physarum actor, here it is, could have sensor angle different from from rotation angle, though. So this could give us some differences in behavior. Also, there is a sensor width. I'm not taking this in account, but actually the way sampling happens, I guess, should influence on should make impact on the behavior we're getting, but whatever. So here I'm creating two matrices for rotation right. This is in radians, I guess. This is for rotation left, and this is the angle for sampling. So as you can see, sampling angle like twice larger than rotation angle. Okay, and here I do samples. Here I do sampling from the left sensor, from the right sensor, and from the forward sensor. And and also I like make those sensors a little bit longer, multiply them by 1.5. And here I'm checking if left sample is the largest one, then we will rotate to the left. If we have the right sensor giving us the largest value, we rotate it to the right. Otherwise, we keep like straight orientation. Another thing that should be parameterized, I guess I should use uniforms to pass some values as a settings to these shaders. Here I do sample of a value in a given, in a actors, in a points position, and I add a particles intensity value to current position, and I do this like in a 4 sub steps. Like I add 1/4 of the intensity, and I move the particle forward. I rotate it actually, and then I move it forward for 1/4 of its direction, or actually it should call speed vector. And I do this thing 4 times. So for faster moving particles, it won't left dots, but it will left it should left some kind of smoother line. And this part should, I guess, be changed. At least a number of steps should be parameterized. And I had to check actually and here and yeah, we're ready to wrap up with this kernel function. So, and if we found ourselves outside of the plane, some of the values are greater than texture dimension, we just like wrap it back. And one thing to notice here, if statements I have all over here, actually not good for shader shaders. I'm not sure if they are not that good for modern compute shader units, but they for sure not good for they're for sure not good for the like fragment shaders. And one if statement could reduce shader performance a lot dramatically. So this thing I should replace with modular arithmetics like division by modulo. These things I have no idea yet how to avoid using if statements here, and this thing to take a third around. All these matrices like should be defined before I have no need to make these computations in each compute function. I guess a compiler could see that this is actually constants. It's quite easy to pre-compute them, pre-calculate them on a compilation stage, but anyway, it's not good to have them here. And also those angles should be passed through user interface. But here we have a compute function where we're doing a particle movement simulation. Here we have a blur function. Actually, it's a basic blur kernel. It's a basic 3x3 kernel from an image processing thing. And nothing fancy. And I guess I could reuse this function should be available as a library function from Metal Kit or Metal Library or something like this. And yeah, one thing I do here is to multiply final output value with a value a little bit less than 1 to have everything decay as particles left this residue all the time. Without this decay, it will just like overflow everything, and everything became white, burnt out, and nothing interesting. Also, this thing should be parameterized, and one thing I want to do is to, maybe that's because I cannot use a standard library blur kernel. I want to define non-uniform blur kernels here, so like it has something like this. It should have like it should have same sum of these fractions, but they should be like not that uniform. So I guess it will produce a little bit more interesting non-uniform blur behavior, like shifting some parts of the residue to the side, like it's like sliding by the force of gravity, or um, some kind of surface tension effect. I do not know. And yeah, simple vertex function, basically pass through, and writing texture, displaying this texture on a plane. Basically, that's it. So, let's have a look one more time on what we have here. I'm not sure if it's visible on stream, like, because of all compression and everything. So let me increase it, and I'll make a pause. So you can have a better look here. Performance, GPU time, dependencies. Actually, these insights were kind of useful. So let's see. Let's have a look at this texture. You see, here we have a fast moving particle. Even we have 4 steps, it still left distinct points that are visible after one blur iteration, but almost invisible on the third iteration. And we have slow moving points, very fast moving points, very slow moving points. And yeah, that's the Physarum we have right now. One thing to fix is you see that the edges of the texture not like shaded. They not have intensity of proper intensity. Even I wrap particles around, so if particle left goes all the way to the left, it will came from the right. But this blurring behavior doesn't take this this property of the space I'm working in into account. And this is because I'm sampling values without checking if this resulting index is out of bounds of the texture. So I need to check. I need to check if it's the case, then I should wrap this thing. And I have to do it with division by modulo. Okay, so let's go to GitHub. Let's create a new issue. So we're kind of formalizing the process. Fix blur behavior. Near edges. This is a bug. Okay. It's not open, it's open. So let's assign it to myself. And how can I start working on it? It's open. I want to make it like in progress. Close command. Okay, so let's define a couple of variables of they would be like indices. Like 0, 0 is top left. It should be index. It's not a half. It's uint. Index x minus 1 One thing to find out is how to do modular division. Let's make sure it works as before. No, it doesn't. I broke something. But what? Does it need like... Come on. Okay. It works as before, with edges being darkened. Okay. So this thing should be solved where we have plus. Should be solved with something like this. Dimensions. Actually, do I spell it right? S, not T. And Let's check. If it works. Actually, let's so the question is what to do with negative numbers. If we have here index at 0 and we got -1, we need 1999 as a result. So we can add dimension here. Times minus. Does it make sense? Let's check. We have 5, 4, 2004 divided by dimensions 4. We have -1. Looks good. See no issues. Fingers crossed. I hope I did my math well here. And let's take a closer look. Yeah, we have it all the way to the edge with no fading. Nice. So this issue is solved. Can commit it. Renderer. Let's not commit this one, but let's keep things clean. Fix blur on edges issue. Issue number 4. Commit. Push. How can I what can I do with it? Mark as fixed. Let's add one more issue about use modulo division particle movement particles. Assign myself. This is enhancement. It kind of works, but not efficiently. Submit new issue. And let's comment these things. And used variable dimensions. Direction, and I need it here. On this, and divide all these things by dimensions. Can we do it like this? No. Okay then. Plus equals. Then let's do it as a second step. So here we have updated positions, and it could be like a little bit do we have this? It sounds. Is it possible? It is. No, it was not possible. Okay, so I guess this one for integers. Okay, let's go and check this reference for what? Metal shading language specification. So it has something called fmod. Or mod f math functions, I guess. This is what we're looking for. 1.2. Mod f. Decompose a floating point number. The mod f function break the argument x into integral and fraction. No. F mod returns x minus y times trunc x over y. If this is what we need, what does trunc do? Trunc rounds x to integral value using round to zero rounding mode. Maybe this is what we need. What was that F mod? F mode. Ouch. And let's move it. Let's try this really fast here. Is that? Okay, we do not have Z component. Okay. No. This is not what I was looking for. I need just a modular division. Why do I have no floating modular division? Mm. What does this mean? Trunk. So we have, let's say, we have F mod 1000 times 300. So we have 1000 minus 300 times 1000. What does this mean? Is trunk of this will be round to 0. It will be like 3 times 3. Actually, it will be 100. Yes, this is what I'm looking for. Actually, let me check this particles behavior one more time, because it looks like no. Oh, they do the right. They works if they move in positive directions, but when the value is negative, this is when the issue happens. So somehow we need to take into account negative values. And we have here it we can make them move to positive. Positive side like this. And it works. This is nice. Now I'd like to implement this behavior for each step, like after every position update. Like this. Let's remove all these things. Okay. Very strange. Ah, yeah, it was not committed. Those commands were not committed. Comments were not committed. So use modular division article position fix number 5. Is this number 5? It is. Commit and push. Also, let's commit this thing. Not need compute. Like this. Did I close it, or it closed because I said it in a commit message? Oh. Nice. GitHub does a lot of things easier. What's next? Next, I'd like to have some break. So I guess I will not pause the stream, but end this one. Maybe we'll get to this sooner. So, see you later. Have a good time.